In the last section, we talked about confidence intervals, which is one way to take a sample statistic and use it to make an estimation about a parameter from the population. Hypothesis test is another way to approach that problem. And we're going to talk again specifically at first about the z-test using the standard normal distribution and to do a hypothesis test about a single mean, but we'll also talk about the general concept of hypothesis test, and as we move through the course we'll do more types of confidence intervals and hypothesis tests. So you'll hear these things called a hypothesis test, a significance test, a test of significance. There's different ways of saying it, but they're all about testing a claim about a hypothesis about the population against your sample data. Okay? And so this could be a claim about any population parameter. It could be a proportion, one mean, two means, more than two means when you do what's called an ANOVA. So there's lots of different hypothesis tests you can do. We're going to start with one about a single mean. So I'm going to, by example, kind of show you how a z-test works without using it in the frame of the z-test, but then we'll formalize it here. Okay. So I'm just going to read through the example here, but suppose we're at a large university that has a really large number of students so that we can think about a large population where we would do a small sample. So suppose we have 1,000 students taking Calculus 1, and suppose, as has to be the case with the z procedures, that somehow we know the standard deviation but we don't know the mean. We know there's a standard deviation of 12 points and we don't know the mean. So we have a very large number of students taking this calculus test. We know the standard deviation is 12, but for some reason we don't know the mean. And as I point out there, and I mentioned, in practice, if you don't know the mean, you probably don't know the standard deviation, and we'll see what to do with that later, where we use the sample to come up with an approximation of the standard deviation. But suppose we take a random sample of 30 students, and we find a sample mean of 65, but the teacher claims that the overall mean is 70. Okay? Now, I don't think a teacher would lie about something like that, but just as an example, suppose somebody claims that mu is equal to 70. You take a random sample and you get that your x bar is 65. Then you might think maybe mu is less than 70. Okay? That's the setup here. And so that's the general setup. You have some claim about mu in the population, and you're going to test whether it's less than or greater than or different from that. In this case, we're going to do less than. Okay? And what we do is we find a probability based on what we call the null hypothesis, which is always the equality claim here, which would be that the mean really is 70. So we can do the z procedures and we can figure out, well, what is the probability that we would get an x bar less than or equal to 65 if the real population mean were 70. And we've got to be careful here too, and when we do it we have to use sigma over square root of n because we're talking about x bar and not x. Okay? So my 2.19, that's 12 divided by the square root of 30. So we know that the mean, if we take a sample of 30 students, we can use the central limit theorem, and x bar would be approximately normal, and the mean would be 70 if that were true. Okay? And then the standard deviation would be sigma over square root of n, which is 2.19 in this case. And we can compute, well, what's the probability that we would get a score less than or equal to 65? And it turns out it's only about 1%. So we could do normal CDF, negative 1e99 to 65, with a mean of 70. And we're talking about x bar, so a standard deviation of 2.19. And it turns out it's about 1%. Okay? So here's the overall idea of the hypothesis test. We've got this thing called a null hypothesis, is what they call it, that in this case would be mu is 70. We have sample data that gives us some evidence against that. So we test what's the probability that we would get a score this low or lower if the mean were 70, and it's only 1%. Okay? So if the mean was really 70, there's only a 1% chance we would have found a 65 or lower, which means we have really strong evidence that the mean is not 70. Okay? That's how the hypothesis test works. We test for evidence against the null hypothesis. If we get a really low probability that what happened in our sample would happen, but it did happen, then we have strong evidence that the null hypothesis is not true. Okay? If we get a large probability, then we don't have strong evidence against it. So suppose that we had a sample mean of 68. I shouldn't say instead of 70, I should say instead of 65 in the previous example. So suppose we still have the claim that it's a 70, but we've got a sample mean of 68. Well, the probability that you would get a 68 or lower if the true mean was 70 is about 18%, which is fairly high by random sampling, almost 1 in 5 that it could have happened by random sampling. And we would say we do not have strong evidence that the claim is false, that it's a 70. And there's an important concept here that we have to get. We're always testing against the null hypothesis, and our results are either that we have strong evidence it's false or we don't. We never say that we have strong evidence to conclude that it's true. We would have to do the entire population to conclude that it's true, but the way we do it by probability, we can have really strong evidence against it or we don't, are the results. Okay, so that was a specific example, but with a hypothesis test, that's what you do. You have some sort of null hypothesis, which is some sort of usually claim of equality or no difference, and they use the notation capital H sub 0, and null is another word for 0 in math, so they call it the null hypothesis, H sub 0. And you're testing that against some alternative, H sub A, for the alternative hypothesis. And we say that could be one-sided or two-sided. It's one-sided if it's a less than or greater than. And we say one-sided because if you draw the picture, it's one tail, one side of the picture that you're looking for the probability from by the shaded area. Or if it's a not equal to, it could be on either side, and they call it a two-sided. It could either be less than or greater than, which would be a two-sided picture. So in the previous example, we were testing the null hypothesis that mu equals 70 versus the alternative that it was less than 70, and using our sample data to test that hypothesis. So here's another example where we just want to set the hypothesis up. You're not going to get any part of the problem right if you don't get the hypothesis correct in the first place, so that's an important part of it. So does job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half of the workers were assigned at random to each of two groups. Both groups did similar assembly work, but one group was allowed to pace themselves while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 more weeks. So you've got a matched pairs set up here. The response variable is the difference in the satisfaction scores, self-paced minus machine-paced. The parameter of interest is the mean mu of the differences. You're looking at the mean difference, self-paced minus machine-paced, in job satisfaction scores in the population of all assembly line workers at this company. State the hypothesis for performing a significance test. Later on, we'll get some numbers and actually do the test, but right now we're just going to state the hypothesis. Okay. In the real world, so you have this choice of doing a less than, a greater than, or a not equal to when you do the alternative hypothesis. In practice, they say you should always do the not equal to unless you have a strong argument for doing a less than or a greater than, because it's easier to find what we call a significant result if you use one direction, because you get smaller probabilities automatically by doing that, because the one-sided is always half the probability of the two-sided because it's half the picture. So in practice, if you're going to do a one-sided test, you have to have really good reasoning behind it. I say in class in these problems, use the wording of the problems. If it says that they think one is greater than the other or less than, or use some of that language, do a one-sided. If it just talks about them differing, just go with not equals to. And that's what this problem says. It says they want to see if they differ. Now, you may have reason to believe that people who are doing an assembly line and they can't pace it themselves might be less satisfied. I don't know, but the problem just says differ. So that's what we're going to go for when we do the alternative hypothesis. The null is always equality, and in this one, often when you do the matched pairs, it's mu equals 0 when you look at what you're doing. You want to know if there's a difference or not when you subtracted the scores. So if you're actually measuring those differences, the null hypothesis would be that the difference equals 0, that mu equals 0, where mu is the average difference. And then the alternative would be not equal to, that mu is not equal to 0. Again, because it just says differ. It could be less than, could be greater than. Okay? So that would be the hypothesis in this case. This is a pretty common setup. You have matched pairs. Your statistic that you're looking at is the difference between like a pre and a post or two different trials or something. And you want to know, is there a difference? So when you subtract, is it different from 0 or is it 0 would be the null hypothesis there. So when we do this, depending on how you do it, you may not see all these values, but there's always, at least in the background, if you're using a calculator or software to do all this, there's what's called a test statistic, which is some measure of how extreme is your sample value compared to your null hypothesis using that distribution. And then you have a probability. What's the probability you would get that type of test statistic if the hypothesis was true, similar to what I did with the calculus example. And so small p-values give you strong evidence against the null hypothesis, because if the null hypothesis was true, it's very unlikely that the sample data would come out the way that it did, but it did, so that's strong evidence against the null hypothesis. Large p-values, we say they fail to give you evidence against the null hypothesis. They're not proof that it's true, it's kind of like inconclusive. We may have some evidence, but it wasn't strong enough to conclude that the null hypothesis is false. So the result is either that we reject the null hypothesis, have good evidence that it's false, or we fail to reject the null hypothesis. Small probabilities that we call p-values, small p-values, we're going to reject the null hypothesis. Large p-values, we fail to reject the null hypothesis.